Hello and welcome to another lecture. So today we're looking at forced oscillations and resonance, which is section 2.6 in the book. We're really looking at part one of it, which is what happens in the undamped case. In which case we will get actual resonance. So there's no damping, there's no friction. It's going to be a forced mass spring setup with no friction. All right, so the book, you can get it at this URL. You can see that in the description as well. You can browse the book on the web. You can get a PDF. You can get a cheap paperback, but you can browse it for free. All right, so what are you doing? So we return to this model where we have this mass on a spring. Where there's some damping. It's as it moves along the floor. It's there's some friction, and now we're gonna add that forcing function, and that's gonna depend on time. There's gonna be different force depending on time. So the equation is well, we've seen this before. M is the mass, right? C, that's the friction. K is the spring constant, and capital F is the force, right? Some external force acting on the mass, right? Maybe somebody's pushing it, or there's a jetpack attached to it, or maybe there's a there's a really loud noise, and this is a pane of glass or something that vibrates. There's lots of places where this comes out, right? All right, so we will consider the simplest periodic force, and that's just a cosine, right? So it's going to have there's some constant in front of it, so that we can, that's how much force, how much sort of oscillating back and forth force there is, and omega is the frequency at which it's happening. So there's some cosine that's just happening. Now, this thing, if we understand this, which is the simplest possible periodic force, we will actually, in some sense, understand all periodic force, because using Fourier series, which is also covered in this book, you can actually write every periodic function using just sines and cosines. And so if you can understand what happens for sines and cosine, and for sine it's basically the same thing. But if you can understand what happens for sine and cosine, you can understand actually what happens for all periodic functions, so periodic forcing functions. All right. So, but let's just do this simple case where we'll see actually, what's happening, right? So if it's a noise from the outside, we're basically, acting on the pane of glass, right? I mean, it's basically just a single frequency noise, right? All right. So we will start with, as I said, an undamped, and the next part we'll look at the damped, where it's a little bit more complicated. So in the undamped case, so there's no C. And so this is our equation that we're looking at. And well, this is, we know exactly how to solve this, right? So the complementary solution is this guy, where omega naught, as the natural angular frequency, is just square root of k over m, right? So we solved this before, right? When there was no force, right? This is just the simplest possible second order constant coefficient equation, right? So that's what we have, right? So we have just these sines and cosines. Now the omega naught is really the frequency at which the mass wants to oscillate without any force, right? If there is no force trying to make it oscillate at some other frequency, this is the frequency that the mass would want to oscillate at, right? Now, first, let's suppose that forcing frequency, the noise coming from the outside, or the jetpack, or whatever is our, wherever our force is coming from, that's coming with a different frequency, right? So let's suppose that omega naught is not equal to omega, right? Now, if omega naught is not equal to omega, then undetermined coefficients will work, and we can just try something of this form, right? A times cosine omega t. Now, you could include a B sine omega t. I mean, if you really followed the undetermined coefficients method just blindly, yeah, you would just do A cosine omega t plus B sine omega t. It doesn't hurt. You could do it. You're just going to find out that B is 0, right? Why? Because there's no x prime here, right? There's just x double prime and x, and so two derivatives of cosine is still cosine. It was was whatever in terms of omega coming out, but there's no sine, right? So, but if you're worried, you can always include it. You'll just find that B is 0. So we find that this is that A is that constant over here, right? So to be able to solve this equation, we have to make that constant be that guy, right? So it's the amplitude of the force divided by the mass times omega naught squared minus omega squared, right? So the general solution is this, right? So that's just, we're just doing what we've been doing all this chapter, right? Just putting everything together, and this is a fairly simple equation, right? So that's what the general solution is. Now we could also write it another way. If you remember, we could rewrite this complementary solution as this, right? And so then we would just have some constant, some amplitude times this cosine wave, which is shifted, right, by gamma, and this cosine wave of this amplitude. So it's really what we have as the solution is two cosine waves at different frequencies and shifted, or possibly shifted, right? They don't have to start at the same time, right? Basically, so that's what the solution is, right? So let's look at an example. Suppose that this is our equation, right? So mass is a half, the spring constant is 8, and our force is 10 cosine pi t, right? Let's suppose that we take the simplest possible initial conditions. So this is basically our omega is pi, right? Omega naught is k over m, right? Square root, right? So it's going to be 4. F naught is 10, right? And mass, as I planned, is 5, right? 0.5, sorry. All right, so the general solution, we just plug that into our, plug that into this that formula, right? So if we solve in this setting, if we solve using the initial conditions, solve for the C1 and C2, we find C1 is actually fairly conveniently this thing, and C2 is 0. So this is what the solution is, right? And here's the graph, right? So notice this so-called beating phenomenon, and that's this phenomenon where you have something growing in amplitude and going down, growing in amplitude, going down, growing in amplitude, going down, and this really comes from this this identity. So if we have if we're looking at if we have these two cosine waves, and let's suppose that they have the same amplitude, and we superimpose them like this, then it's really a sine wave with this frequency times a sine wave with this frequency, And so you have a small frequency sine wave modulated by, or really a high frequency sine wave modulated by a small frequency sine wave. The small frequency sine, the slow frequency, right? I mean that's the beating that you hear, right? The fast frequency is this guy, right, over here, right? And so that's what's going on here, right? It's this guy can actually be written like this. So it's you know the slow thing, the thing that's out here, that's this guy over here, right? Uh, and the fast guy, the high frequency guy, uh, that's this guy, right? So that's the guy that wants to move like this, but it's modulated by this guy. All right, so that's sort of the general phenomenon that you see here. I mean, you know, in general, you know, if it's not as simple as here, then uh, you know, they might not have the same coefficients in front, so you're gonna get something slightly more complicated. But that's the general idea, that you know you get this sort of beating behavior in there. So all right. So you can already see that it's that you know, this is how the mass is moving, right? So in this case, you know, the mass is moving, and it's sort of going out very far, and then it slows down, and then it's going out very far, and then it slows down, and it's going out very far, and then it slows down. So so you can see that the behavior is already more complicated than you know, than without forcing, right? When it was just a single sine wave. Uh, So that's just what I said. All right. So now, what about the case when the frequencies are the same? When the forcing frequency is the same as the natural frequency? So here we suspect something will blow up from this term over here, right? We have an omega naught squared minus omega squared. Well, if they're the same, that's 0, and so we'd be dividing by 0. So you know, the previous solution doesn't work, right? You know, we can't divide by 0. So you know, but what we're suspecting is that well, if omega and omega naught are not quite the same, but very very close, then we're dividing by something very small, which means that this amplitude is very big, right? So let's try to solve it. Undetermined coefficients. Well, it says that basically we should try something like this. In this case, we do need the sine term because of that t, we will get in the derivatives, we'll get sines and cosines. So we need to put in all of that. And so we plug that in. You know, plug this guy into here, and this is you know, this is what we get, right? And by the way, notice that I've divided by m both sides, just for convenience. So we plug that in, and we try to figure out what we get, and we find that a is 0 because there's no sine term on this side, right? So this just disappears, and 2b omega is supposed to be f naught over m, so b is f naught over 2m omega. So that means that the particular solution is, well, I just take that b, put it in front of, you know, here. This is not there, right? So that's our particular solution, right? And the general solution is this guy over here, right? So this is the complementary solution, and this is the particular solution. Now, note the t here. Note the t out here, right, or out here, right? Well, what it does is makes the particular solution grow without bound, because basically, what is the you know, what is the amplitude, right? It's this guy. It has a t in it. So as time grows, the amplitude grows. it becomes faster, bigger and bigger and bigger and bigger, right? And so what we so it oscillates between these two guys, and that becomes bigger and bigger. Whereas the complementary solution, well, I mean, just oscillates between theirs, well, whatever it is, but it's constant. It doesn't change. So eventually, we're only seeing this bit, but not just that. It's becoming bigger and bigger, right? The longer things go on, the larger this oscillation is, right? By the way, you can see that already in the beating. So let me go back there, right? So this slow oscillation, right, which is it's really this we're subtracting the two frequencies. Well, if they're very, very close, that's really just becomes sort of this really really long sine wave. It almost looks like that T, just a straight line. I'm sort of, if you're zooming in onto what happens near the origin at the sine wave, it really just looks like it's like a straight line with slope. Well, it's just the sine, just slope 1, right? So really, it's this thing, this part of it, and we'll just see that sort of going on forever as if the omega is equal to omega. So let's see an example of this. So with these constant, doesn't really matter what they are, but we're taking f naught is 2, mass is 1, and omega is pi, right? We'll get this particular solution, right? I mean, I've set the C1 and C2 to be 0. So here you have the solution, and then you can see what I was saying with the beating, right? It's sort of take that first part of that beat, but stretch it out to infinity, and that's what we're getting, and it just keeps growing, right? It's sort of that sine wave also has sort of infinite amplitude, right? It becomes bigger and bigger and bigger and bigger, but it's sort of I'm not really seeing a sine wave. I'm just seeing this thing, right? I'm just seeing the T, really. That's the slow oscillation, which is really just frequency 0 now, right? But that's what I'm seeing. It's just bigger and bigger and bigger oscillations, right? So that's called resonance, right? Or pure resonance in this case. When I really can get arbitrarily high arbitrary big oscillations, right? Just by waiting enough, right? So that's what resonance is, right? Now, resonance can be good and can be bad. It can be good. We can create large oscillations with little force. We don't have to. We just have to sort of apply the force. Basically, we don't have to apply it all at once. We can just apply it in little bits, right? So if for example, if you're swinging your child on a swing, right? You don't have to, just give one push. You can give many pushes, and then you can make your child, swing very far out, right? Even if you have a very heavy child, right? You can make the child swing just by pushing very lightly, right? Just doing it enough, right? Or another example is quartz watches, right? If you have a watch, right? There's a crystal in there, and it's it resonates at a certain frequency, at a very specific frequency, and so you can use that to measure time. Other examples are like NMR, magnetic resonance. It even has the R in there. MRI imaging. It's again R is resonance. So this is in chemistry with NMR. Chemists will use it to figure out what compound they have by using resonance. And MRI doctors will look inside you by using resonance. So resonance can be very good, right? That something resonates at a very specific frequency. Some system. If I'm applying some force, I can basically, if I move the frequency that I'm applying, I can see where it starts oscillating, basically, where it starts resonating, right? Because that's when the oscillations will become very, very large. But resonance can also be bad, right? So, for example, in earthquakes, if there's resonance in buildings, they can collapse, right? Because the earthquake might not have each oscillation of the earth, right? Might not have so much force, but if they're just at the right frequency, some building might collapse. And some other building right next door won't collapse because, well, it didn't hit the right resonance frequencies there. Um, Vibrations in engines, right? That's another one. I mean, you get a very sort of consistent, some vibrating force, right? And if there's some other part which starts resonating, right? That can either just be annoying, right? You hear the resonance, or it can actually take the car apart, right? There's even an example where soldiers marching on a bridge with a very fixed rhythm have caused the bridge to collapse because it hit the resonance frequency. All right, so next time we'll look at what happens when there is some friction, because well, in real life there's always some friction. So you can think of this as a sort of an approximation of the setup when the friction is very, very low, right? So we'll see what happens when we start adding friction. So you don't get so-called pure resonance, you get practical resonance. So if the friction is sufficiently low, then you will get something that looks almost like resonance. Or the resonance might completely disappear if the friction is high enough. All right, so we'll look at that next time. All right, so see you then.